Hello and welcome back to the Maths Behind the Economics YouTube channel. This is video 11 in the Logs for Economics series, and in this video we're going to discuss what happens when we have roots behind the log sign. So again, I'm going to remind you of the rule. Then we will discuss why the rule works, and we will have examples and practice questions as always. Let us get started. Here are the rules with some special cases. So if I have got a root behind the log sign, then the log can be replaced by the log with the argument without the root over the root itself. The special case when I would replace the base with e would be ln nth root of x, which should be equal to ln x over n. Now what would happen if in the argument I wouldn't only have roots, but I would also have an exponent? Well, in that case, the exponent comes out in front of the log sign, but then the root will be underneath in the denominator of that log sign. And again, if I replace the base with e, the natural logarithm, it will give me ln nth root of x to the m being equal to m times ln x all over n. Let's try to convince us that it works with looking at some examples. And for that, we'll need a bit more space. So, can I use log base 3 cube root of 5, which I know can be replaced as log base 3 5 to the 1/3? Is this equal to 1/3 log base 3 5? Well, from the previous video, we might be tempted just to apply the rule straight away. However, there is a caveat. In the previous video, we only proved that the exponent can be brought down in front of the log when that exponent was a positive whole number. Remember, n was a positive whole number. Well, 1/3 is not a positive whole number, so we cannot apply the previous rule straight away. It is incredibly important that we know what the assumptions are in any of the mathematical rules, identities or theorems we are trying to use. If we apply a rule to a situation that violates the assumptions, the rule will not hold. So, as I said, n is a positive whole number. Strictly speaking, we looked at n being a negative number as well, because we showed that log b extra negative n is also equal negative n log bx. So we could use something like log base 2 x to the negative 3. That will be equal to negative 3 log base 2x. That's fine, but still is whole numbers, not fractions like we have it here with the 1/3. So make a bit more space and then enlist the help of the calculator just to have an idea whether we can even hope that the rule works. So look at log base 3 cube root of 5. Now, if I use the calculator, this is going to be equal to 0.883245069, and I copied down every single one of the digits that the calculator gives us. Also, I can put into the calculator 1/3 of log 3 5, and the calculator will give me the solution of 0.883245069. Well, that's hopeful because the calculator gives me the same solution. However, I need to keep in mind that the calculator rounds to the nearest 15 digits, so I don't know what the 16th digit is, and they could be slightly different. So in theory, I could have a 2 here while a 3 here, and then the two things wouldn't be equal. So, while using the calculator gives us hope, this is just one specific example. Let's look at another example. Log base 2 fifth root of 3. Using the calculator, I'm going to get the solution of 0.3169925001. And if I use the calculator again and calculate 1/5 of log base 2 3, the calculator will give me the number of 0.3169925001. Again, This is hopeful because they are the same to 15 digits, but I mustn't forget that this is just an estimation. I don't know the 16th digit because my calculator is not detailed enough. So we need a formal proof so we can convince ourselves and everybody else that this rule works and it can be used with any base and any roots. Again, make some more space and lay the groundwork. So why should this rule work? Again, we need to establish what numbers we can use with our logs. So again, remember the base always have to be positive and it cannot be equal to 1. If you've forgotten why, then check out video 2 in the log series. And again, our argument has to be a positive number. I again refer you to the second video in the series why these criteria have to hold. And remember, in the previous video, we established that if n is a positive whole number, then we can call that log bx to the n is equal to n times log bx. Now, just to reinstate, our problem is that 1 over n, which is basically our nth root, it's not a positive whole number. So we cannot apply the rule that we derived in the previous video. Even though we established in video 7 in the exponent series when we discussed roots in details that this n itself is a positive whole number that is bigger than or equal to 2. Remember, we talked about the square root, the cube root, the fifth root and whatnot. However, still, when we talk about 1 over n, that is not going to be a whole number. So what are we to do? Well, the good news is by the end of the exponent series, we define the exponent for all real numbers. And remember, logs are a different way to look at exponents. So maybe the logarithm definition will help us out here. Let us go back to the basics and try to prove the identity using the definition of the logarithms rather than applying some of the rules we already had. So let's start again. Let b be a positive number. That's not equal to 1. That's going to be our base. Let x be a positive number and now define n as a real number. Well, real numbers are whole numbers, fractions and the like. So if we define n to be a real number, we will be able to apply the rule, should it be true, for any kind of numbers. So remember from video 6, we know that b to the log bx to the n is exactly equal to x to the n. And here it doesn't matter whether the n is a positive whole number or not. That's by the definition of the log. But now we also know that b to the log bx is just equal to x itself. Now let us make some space. And if I switch the sides of the above equation, I can write x equals b to the log b of x. Now, let us raise both sides to the nth power. What's going to happen in here? Well, x to the n is just going to be x to the n, but on the right-hand side, I'm raising a power to a power, so what I need to do is multiply the exponents together. So b is going to be raised to the n times log bx power. But from here, we established that x to the n is also equal to b to the log bx to the n. So I've got two equations. The left-hand sides are equal in both of them. Therefore, the right-hand sides have to be equal too. So I can derive that b to the n times log bx have to be equal to b to the log bx to the n. And again, due to the properties of the exponent function, when we know that b is bigger than 0 and b is not equal to 1, so basically it's being monotone and continuous, which I understand that these are concepts we haven't discussed in details, but we will do so in further videos. We can now conclude that if the bases are equal, then the exponents themselves have to be also equal. So that's going to give us n times log bx have to be equal to log bx to the n. Now, it is very, very important that we had used no restrictions on the nature of the exponent behind the log in this proof. What we did, we use the definition of the log rather than some other already established rules when we relied on some specific cases of the exponents. So now we can claim that this rule works for positive and negative whole numbers as well as fractions in the exponent. It works for all of them. So we can claim, and I'm going to make a bit more space for this claim, that all of these 7 rules are just special cases of this one rule of log base b x to the n being equal to n times log base b x. So if we replace the base with e, then we're going to end up with the special case of ln x to the n being equal to n times ln x. If we use the 1 over x to the n, which I like to remind you, that is the same as x to the negative n, then we can just bring out the negative number in front of the log. Again, if we replace that base for e, again, not forgetting that 1 over x to the n is x to the negative n, then again, we can just bring out the power in front of the log. Remembering that the nth root is just the 1 over n power, then we can bring out that 1 over n in front of the log, and now multiplying the log by the 1 over n, just gonna simplify down to log over n. If we replace the base with e, we're just gonna end up with ln nth root of x being equal to ln x over n. And if we have got an nth root of x to the m, that is just m over n power. And I can bring that out in front of the log sign, and if I tidy the expression up a little bit, I'm going to end up with m times log bx over n. And again, the last special case is using this rule for the specific case of the base being replaced by e. So I can use the ln nth root of x to the m being equal to m times ln x over n. Talking about killing 7 birds with 1 stone. Okay, more than enough theory for one video. Let's have a look at some practice questions. And as always, we need some more space. So practice questions. Let's look at our first practice question. So log base 10, 5th root of 500 plus log base 10, 200 squared. First, what I noticed is that the 5th root of 500 is 500 to the 1/5, so 500 to the 1/5, and therefore I can bring out the 1/5 in front, and that's going to give me log base 10, 500 plus the 2 from the exponent of the 200 can just come out straight, so 2 times log base 10, 200. Now, the next thing I've noticed, I'm going to keep writing over here, I'm going to keep the 1 over 5, is that 500 is equal 5 times 100. Now, why do I want to do this? I want to do this because 100 is the square of 10. So I will be able to replace log base 10 100 with 2. So I'm going to rewrite this as log 5 times 100. And I'm going to do the same for 200. In a sense that I'm going to replace that with 2 times 100. Okay, keep going. Now I can apply the log multiplication rule. So it's going to be 1 over 5 times log 10, 5. And I'm going to keep the bracket here. Plus log 10, 100. Plus 2 times log 10, 2. Plus log 10, 100. Okay, I've got a bit more space in here now. So again, I'm going to make sure that we understand that these are side calculations and they don't belong to the equations. So what I've got here is 1/5 times log base 10, 5 plus 1/5 times log base 10, 100 plus 2 times log base 10, 2 plus 2 times log base 10, 100. Now, in each case, the log base 10, 100 can be replaced by 2. And again, I can do that because 10 squared is equal to 100 and the log is always looking for the exponent. So I've got 1/5 log 10, 5 plus 1/5 times 2 plus 2 times log base 10, 2 plus 2 times 2. So let's make the numbers nicer. So this is just 2/5. This is 4. So what I've got here now is 1/5 log base 10 5 plus 2 times log base 10 2 plus 4 and 2/5. If I wanted to, I could replace that with just one fraction, a top-heavy fraction. As it stands, I can leave it as a mixed number as well. It makes no difference. Now, whether you want to go further and manipulate these two and see whether you can make it slightly simpler is up to you. I think I will leave it in this form for today's video. But if you have worked with it and you come up with a simpler version, leave a comment underneath the video. Right, we used up quite a bit of space. Let's move again. So let's look at practice question 2. I've got log base b k squared plus 3 times log base b square root of k minus 5 times log b k. Now, in this case, I've got two choices. I can either bring down the roots and the exponents, or I can bring up the numbers in front of the log signs. And just because I can, I think I'm gonna go with bringing down the exponents to multipliers. So let's do just that. So the first term will be 2 times log bk plus, remember the square root of k is the same as k to the half, so I can bring out a half multiplier in front of the log sign. But a third times a half just gonna give me 3 halves. So it's gonna be 3 halves log bk minus the last term doesn't change. That's just gonna stay minus 5 log bk. Okay, so let's keep going with the calculation. What happens in here now, I've just got log bk, log bk, log bk multiplied by some different numbers in each 3 of those terms. So for a moment, if I just think about log bk as a quantity, whatever, like apple, then what I've got here now, I've got 2 apples, but 3 half apples, and taking away 5 apples. So 2 and 3 over halves makes 3.5 together, which is 7 over 2 log bk. But I have to take away 5 of those log bk's from it. So altogether, I'm going to end up with negative 3 over 2 log bk. And I hope you agree with me that this final version, minus 3 over 2 log bk, is much simpler than what we started with at the beginning of the exercise. Let us move on to the third practice question, and that is going to be log base 5a cubed minus log base 5 1 over a squared minus log base 5a to the 4. Again, I've noticed that there are exponents behind each of the logs, and I can bring those exponents down in front of the log signs. So first term is going to be replaced by 3 times log 5a. The second term, remember that the 2 is in the denominator, so it's 1 over a squared. 1 over a squared is the same as a to the negative 2, so we can bring out a negative 2. So it's going to be negative 2 log base 5a minus the last term is just 4 in the exponent, so I can just bring down the 4, and it's going to be 4 times log 5a. Now, like in the previous example, now I have got just log 5a in each of the terms, so it's the same quantity in each of the terms. Again, I can think about it as 3 times something, take away a negative number, that I can be replaced by positive 2. So 3 of something plus 2 of something, take away 4 of something, altogether is going to be just 1 of those somethings. 3 plus 2 makes 5, take away 4 makes 1. So I'm just going to have 1 of those somethings. And what is that something? That is just a log 5a. Well, I hope you agree with me that this is a lot simpler than this long expression. Some more space. And then question number 4. ln 1 over x squared plus ln x cubed y minus ln cube root of x squared y cubed. What is this going to be equal to? Well, the first thing I've noticed is that in some of the log arguments, I have got a multiple of x and y's to different powers, but in the first one, I don't. So it would make sense to break the logs into terms which have got x's in one argument and y's in other arguments. So let us do just that. So the first term is only x in the argument, so I'm going to keep x, but I'm going to replace 1 over x squared with x to the negative 2. Plus, there is a multiple behind the second term in the log sign, so I can break this out as ln of x cubed plus ln of y. In the next term, which is a subtraction, I'm going to have to therefore put in a bracket because this subtraction applies to the whole log sign. So in the last term, I have got a multiple of cube root of x squared and y cubed. So I'm going to replace that as ln of x to the 2/3. Remember that root becomes the denominator in the exponent plus ln of y cubed. Okay, let's see what else we can do. Well, we can bring down the negative 2 in front of the first ln. So it's going to be negative 2 ln of x. We can also bring down the 3 in front of the second term. So it's going to be plus 3 times of ln x. The ln y just stays on its own. But now I have got negative signs. So I have got negative, the 2/3 can be brought down. So negative 2/3 ln x. And again, the negative sign have to apply to everything inside the bracket. So that's going to be negative. And the 3 can be brought down in front. So that's going to be negative 3 times ln of y. So what we're going to do next is we're going to try to collect the same things. So I have got ln x and ln x and ln x in these terms. And the remaining 2 terms are just ln y's. So I've got negative 2 plus positive 3 of the same thing. That's just one of that thing. So these 2 just cancels down to ln of x. But I've got negative 2/3 ln of x still to take away. So ln of x and this negative 2/3 of ln of x just going to cancel down to 1/3 of ln x. What happens to the ln y's? I have got 1 ln y and I have got negative 3 ln y. So altogether they're going to cancel down to negative 2 ln of y. Now I can replace them and the final answer to this long expression will be 1/3 of ln x minus 2 ln y. Last question for the video, number 5, ln 2x minus ln x cubed plus ln y over x cubed. Okay, let us make a bit more space and let's get started with this example. Now again, every time in mathematics when you try to solve a question, you have got many different ways to go down. And some of them will be slightly faster than others, but in every single case, if you do the correct manipulations, you don't make any mistakes, you will always end up with the same solution. So just because I can, what I'm going to do, I'm going to bring down the exponents from behind the log signs first and then see what I can do with them. So I'm not going to do anything for the first term, so I'm just going to keep that as ln 2x. But in the second term, I can bring down the 3, so that's going to be minus 3 times ln x plus 3 times ln y over x. So next thing, I have got a multiple behind the log sign in the first term, so I'm going to turn that into ln 2 plus ln x. The third term stays as minus 3 ln x plus 3 times ln y over x is going to be ln y minus ln x. Remember, we're using the division rule here. So plus ln x minus 3 ln x is going to be minus 2 ln of x. So the first term doesn't change, it's ln 2 minus 2 ln x. But here now I have to multiply a bracket by 3. So that means I have to multiply both the first term and the second term by that 3. So that's going to be plus 3 ln y minus 3 ln x. Okay, so what do I have altogether? Well, I still have got negative 2 ln x and I have got a negative 3 ln x. ln 2 just stays as it is, and remember that ln 2 is actually a number because I know the base is e, and I know the argument, so that can be replaced with a specific number if I wanted to. But because that's always going to be a rounded answer and I prefer the exact answers, I keep ln 2. Then the two highlighted terms will cancel down to minus 5 ln x, and the plus 3 ln y stays. Now, depending on if I need the solution and logs with individual arguments, or if I wanted the answer as a single log sign with an argument of expressions behind it, I could stop here, or I could go and do some further manipulations. Let's have a little bit more practice and see if I could make this into one log sign. So, as I said, you can stop here, and this would be a perfectly valid answer. But just for the sake of practice, let's do a few more calculations. So, this is going to be ln 2 minus ln x to the 5, I can bring the 5 up, plus ln y cubed. Now, why did I have to bring these 5 and 3 up into the exponent? Because the multiplication and subtraction rules only apply if there is nothing in front of the log signs. So now I can apply the division rule for the first two, and I can replace that with ln 2 over x to the 5 plus ln y cubed, and that's gonna give me ln 2y cubed over x to the 5th. Well, this is quite concise, but this is maybe a little bit more sense. We might be able to understand the longer version a little bit better than the shorter, more condensed version. It really depends on what you want to do with it next. In either case, I hope you liked the video. I hope you fully understand now why and how we can bring the exponents down from behind the log signs. I also hope that you learned something from about proofs and assumptions and when we can use certain identities and theorems. In the next video, we're going to cover how we can change the base of any logs, simply because the next two rules that we listed in our log rules video, the same base and argument, was covered in video 5, and the rules that refers to what we do with the logs when the argument is 1 was covered in video 6. So, I hope to see you in the next video when we're going to look at how to change a base of a log. Thank you for watching. Bye.